Okay, so this is Green River College lab, let's see, number 3, and the Changing Motions lab. And so, this is the lab we'll be doing. And one thing that I want to point out is this little note down here that says, a note on language, I will interpret increasing slope to mean that the slope itself is increasing, not a slope such that it causes the values to increase. In other words, if I have a curve like this, the slope is increasing. If I have this, the value is increasing, but the slope is constant. Okay, so when you use the term increasing slope, this is what I will interpret it as, not this. Okay, and just generally, I would say be careful about when you use the term slope and when you use the term value. I get some students that are carried away with the term slope and write some very strange things as a result. So, so when you do the analysis, be careful of your language. All right. So the first thing here is a prediction. So what's going to happen here is, okay, for activity 1, anyway, I'm going to put a board here and put my cart about there, and then I'll let go of my cart. The cart will roll down, get caught in the cart catcher, and that means that there's 3 portions of the motion. The first portion, where I'm still holding onto the cart and just newly releasing it. The other portion where it's going down the cart, down the ramp unimpeded, and then the third portion where it gets caught by the ramp. So basically, there's something that I'm going to call the region of interest. The region of interest is when it's going down the ramp unimpeded. When we look at the graph, we need to identify when it is that I'm still in the process of releasing the cart, because we don't care about that. This is what we care about, but we don't care about what it's doing when it's hitting the cart catcher. Okay, so basically, when you're making this prediction, what you're trying to imagine is what graphs of the position, velocity, and acceleration would look like if the during the region of interest and ignoring the other regions. Okay, so a couple things that I just want to write up here to remember, and that is, okay, so for a constant velocity, we need darker pens. Okay, for constant velocity, we have v equals delta x over delta t. For constant acceleration, we have a equals delta v over delta t. And so a thing to keep in mind is that if we have an acceleration, that means that the acceleration is going to be the slope of the velocity time graph. Okay, and so again, okay, if this if this is the position time graph, okay, well, my velocity is change in position over time, So that's going to, so the velocity is the slope of the, whoops. Would it help if I did the things properly? Okay, well, so basically, I have a shallow slope here. That means the velocity is small. Well, I have a steep slope here. That means the velocity is getting bigger. So we're getting, here the slope is increasing. The slope is the velocity. So in this case, the velocity is increasing. In this case, if I have a velocity time graph, the value of the graph increases, so that means the velocity increases, but the slope does not. Okay, all right. So yeah, and the acceleration is the slope of the velocity time graph. All right. So keeping that in mind, let's go on to the first exercise here. In which case, okay, so in which case now we need to start the Logger Pro. Okay. Okay, actually, I think I'm going to increase my time to 5 seconds here. So let's do that. Let's see. Okay. And I think that will make things a little bit clearer. Okay. Do this again. There we go. Okay, so things to notice. One, notice that right at the beginning, everything's flat. And so what that's telling us is that I'm not moving yet. This is that first kind of motion where I'm holding the cart still and nothing's happening. But then my position starts increasing, my velocity starts increasing, and my acceleration is now suddenly non-zero. So that's telling me that the cart is just moving freely down the ramp. And then notice what happens here with the acceleration and the velocity and the position graph. So essentially, at about 3.2 seconds, maybe we should make it 3.2 seconds here. That's when the cart catcher starts catching the cart. So I'm going to say, okay. So it says use the acceleration graph to tell when the cart is released. Basically, every time we go down one, the sensitivity increases. So, can we see the cart catcher catching the cart here? Kind of. Here, even, before things really register here, we can see it, registering here. But before it registers there, it registers there. So essentially, the sensitivity is greater with each graph. And so we can better see where the cart is being caught by the cart catcher. And so, yeah, I could say, let's see, each of these is 0.2. So, really, the cart catcher starts catching the cart at 3.4 about. Okay. And then, let's see. Okay. So that's when that's the second thing here. When it was released. Okay. So we can see the acceleration increasing, but it really, we can say that it's really properly moving freely when my acceleration is pretty much horizontal. So that's at about 0.6 seconds that the cart was released. All right, so data at the beginning. So we want the time and velocity at the beginning of our region of interest, and so let me do that. Let's hit Control E, and that will give us our data here. And so let's see. I said about it, 0.6. Okay, so at time about 0.6, we can say that our initial position is about 0.182. Our initial velocity is about 0.088, and our acceleration is about 0.373. I don't think I asked for acceleration, but there it is. Okay, so I'm going to move my cursor, if I can, over to the other side. And I think I don't like this little thing, so I think I'm going to take the time, make the time 3.2 seconds just to avoid that little bump there, and say that okay, my position now is 1.273 meters. My velocity is 0.757 meters per second, and my acceleration is 0.341 meters per second squared. All right, so now we've got the data for that. Okay, so in the next set of questions, it asks about constant velocity versus the above graph. So basically, these graphs that we've just taken, they are the above graph, and so it's like, okay, what does a position graph look like with constant velocity? I expect you to figure that out. The above graph, we've got we've got this graph, and you could ask, okay, how do we tell velocity from a position time graph? I mentioned that earlier in the video, so look at that. Here in the velocity graph, in the above graph, obviously my velocity is increasing, so so it's not a constant velocity graph, so describe what it is, and the same way with the acceleration. So figure out what the what's going on, what would go on if the velocity had been constant, and contrast that with what we're actually seeing here. Oh, and I would also say I want descriptions. If you want to put illustrations to supplement your descriptions, that's great. I encourage it. But I don't want illustrations alone. I want actual descriptions of what the various graphs look like. Okay, so we've got questions about what the features of the graph imply. So I'll let you look at those graphs. Figure out the appropriate answers to those questions. How would you calculate an acceleration by using a velocity graph? Hint. Okay, and then we'll use the velocity graph data to that we just recorded. In other words, this data is what you're going to be using to do this calculation. Okay? All right, so then, for this question, okay, things to note, time is going in this direction. So, the cart starts here, then goes there. So basically, you're going to put arrows between the carts. and then you're going to use those arrows to come up with an arrow that represents acceleration. Now notice that we go from time 1 second to time 2 seconds, so our change in time is going to be 1. All right, so that means that okay, my change in time is 1 here, so that doesn't do anything for the numerical value of what's going on. So we're just going to concentrate on change in velocity. And change in velocity, we're using standard notion as to what change means. Final minus initial. So that is how we deal with this. And yes, we're actually using geometric ways of dealing with vectors in the for this problem. Okay, and remember, do it non-numerically, do it geometrically, show your work, and I want you to explicitly show the connections between the arrows you drew up here and the arrow that you're going to draw for the change in velocity. An equal sign is not an explicit connection. I want geometry. Okay. All right. So now what we're going to do is put a second board up here. Okay. And get our cart and do this again. Okay, so the question then is, how are these graphs different from the previous graphs? So, so again, I'm going to get you some data here. You'll be graphing them. The cart here, using the acceleration graph again. Control E. There we go. Okay, using the acceleration graph again, and maybe moving this somewhere else. Okay, so I'm saying that, the release was complete at around 0.7 seconds. At 0.7 seconds, we have a position of 0.185 meters, 0.094 meters per second, and acceleration of 0.534 meters per second squared. Okay, and then looking at where it ends. I'm going to push it a little and say, okay, I've got, maybe I should go here and say, the cart catcher starts influencing things at about 2.5 seconds, in which where the position is 1.236 meters, the velocity is 1.083 meters per second, and the acceleration is 0.609 meters per second squared. And so, and that's a little bit higher than normal. The normal seems to be fluctuating somewhere, I guess, a little bit less than 0.55 as far as the acceleration is concerned. Okay, but you'll use those. You'll use that data to do your calculations. You'll be looking at the differences, and you'll be using the velocity time information to calculate an acceleration. Okay, so now, here. Okay, so now I've got a ramp that's tilting up. And okay, so what I'm going to do now is I'm going to, well, essentially do this. Maybe I'll do it a little harder when the time comes. But you know, the region of interest is while it's, you know, going up and down the ramp. Okay, so let's see if I can get a reasonable set of data here. Ow, I screwed up. Go ahead and hit collect again. Thanks. Oh, sweet. Moo, no, not so sweet. Something went wrong. Looks like I got in the way of the motion detector or something. That's strange. Okay, well, let's go ahead and do it again. Okay. You know, not quite as good as well last time in terms of the motion of the cart, but you know, I specify most of the way, and I think I got it most of the way. So I think this is the data we're going to use. All right, so let's go ahead and take the data, and I need to remind myself of what I need to give you. Okay, so all right, so again, hitting Control E. All right, so using now notice this time my acceleration is pretty horizontal, you know, around there. We got a touch screen here, didn't realize that. Okay, so I'm going to say that it starts at around 0.8 seconds, in which case our position is 0.443, the velocity is 0.983 meters per second, the acceleration is negative 0.593 meters per second squared. Okay. And then at the end here, which I'm going to say is about 4.1 seconds, my position is 0.457 meters. My velocity is negative 0.884 meters per second, and my acceleration is negative 0.346 meters per second squared, which I don't know why, but there it is. Okay, so then it asks for the data for the turnaround point. So let's find that. Okay, so it went up, it started coming back down. The turnaround point was when it was farthest away, which means it's the highest position on the position time graph. So let's go back and forth a little bit. Okay, looks like the highest position is at 2.4 seconds. Very, very convenient. That's a nice single decimal place number of seconds. The position itself is 1.243 meters. The velocity is 0.018 meters per second, and the acceleration is negative 0.697 meters per second squared. Okay, so here's the thing about this. When the logger pro is taking data, it takes data at a certain rate, which means that it might not actually have taken a data point at the exact turnaround time. Okay, so when looking at this, keep in mind that you know, my numbers here might not be completely exact, and you know, if we want, you know, and we can perhaps understand more conceptually what's going on in terms of the exact turnaround time. All right, so then you'll be asking to describe differences, and and one point, and I think that's been true for all the descriptions so far, but I want to emphasize it. It says describe differences other than the duration of the region of interest. Okay, so if you're thinking, oh, it you know, traveled its distance in less time, that's the duration. I don't want to hear that. I want you to look at other things that tell you differences between, you know, positions and velocities and accelerations. Oh, and limit your description to the region of interest. So, I mean, you know, like I was saying, this stuff, this stuff, this stuff, this stuff, this stuff, this stuff, none of that is in the region of interest. So if you're describing, you know, accelerations going up, I'm going to count off for that. So you know, stick with just the region of interest. And that's actually an important thing to keep in mind for all of the questions that you'll be answering here that are worded that way anyway. Okay, so you know, what features in each graph alone and within the region of interest show when the cart turns around. Okay, so here's the thing. If you're tempted to you know, say look at this graph and make reference to this graph, no, it's each graph alone. So if you didn't even know about these and you were just looking at this, would it tell you where the where my object turns around, and specifically what features of the graph tell you that? And here's the thing. If you were just looking at that alone, then for all you knew, I would have moved my cart like. If I had done that, then my turnaround wouldn't have been in the middle of the graph time-wise. Okay, so you can't necessarily use the fact that, okay, it's halfway in between, because if all you knew was that acceleration graph, then you wouldn't, you know, you wouldn't know that the motion was symmetrical. This graph, yeah, this graph is kind of telling you the motion is symmetrical. This graph, if you know how to interpret, is telling you that it's symmetrical, at least in some ways. This graph, not so much. So if you're trying to figure out from this graph alone where the object is turning around, the question is, what features of the graph would you use? And you know, I would say the same thing about the next few problems. Let's see. And yeah, and then you would you look at the graph and say, okay, it's my. Well, actually, I guess I could do it this way. Say, all right, if I look at my acceleration data. Okay, it's kind of, yeah, it's fluctuating a lot. It's kind of hard to tell what an average would be here. but it looks to me like it's kind of fluctuating maybe around 0.6 or something. It goes way high then way low. What can you say? If we were doing this properly, we'd be doing it with an air trough, but we don't have those readily available to us. So we're going to get this shaky data as a result. Okay, and then we've got another one of these questions, and with this one, the thing to keep in mind is time is going this way. That, you know, my cart starts here, goes to here, and then goes to there. So keep that in mind when you draw your arrows and when you do your analysis. Okay? And then finally, the last page here. And this last page, you're supposed to figure out what the graph, you know, given what we've done, figure out what the graph would look like if we had an object that was traveling toward the motion detector and slowing down. So so put your thinking caps on and figure out what those graphs need to be. All right, so that's the Changing Motion Lab. I'll see you next time.